Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This lecture is on basics of time series analysis. And for this lesson, I'm going to cover very basic concepts of statistics. This is a list of concepts that I'll briefly cover in this lesson. If you do not have a good understanding of these concepts, I recommend you review them before starting on the lectures for this course. The topics that are important for this course include moments of a distribution, which fully characterize a distribution, estimation methods of parameters and statistical models, including method of moments and maximum likelihood estimation, basic estimators, for example, for the mean and variance of a random variable given its distribution, multivariate distributions along with an understanding of the difference between marginal, conditional, and joint distribution, and very important for this course, statistical inference, including confidence intervals and hypothesis testing. What are the moments of a distribution? For a random variable x with density function f of x, the nth moment of the distribution of x is the expectation of x to the nth power, or the integral of x to L, to the power L, times the density function. Similarly, we can define the L central moment, which is the expectation of x minus the mean of x to the power L. Thus, for this moment, we center the random variable to its mean. Two classic examples of moments are the expectation and the variance. The expectation is the first moment, and the variance is the second central moment. Other examples include the skewness, which is the third central moment divided by the standard deviation at the power 3, measuring how symmetric the distribution of x is. Another example is the quartices, which is the fourth central moment divided by the standard deviation at the power 4, measuring how fat the tails of the distribution are. Note that in this slide, I describe the moments assuming x has a continuous distribution. We can also define moments for discrete distributions. In this class, we primarily focus on continuous distributions. Statistical estimation refers to identifying a function of the random data, also called statistic, to be used in obtaining approximates or estimates for one or more parameters or statistical summaries of a distribution. Thus, first we start with realizations or observations denoted with small letters, call them x1, x2, xn. These are realizations of random data denoted in statistics with capital letters, big X1, big X2, up to big Xn. The random data or random variables x's are assumed here to have the same distribution, which is f of x with the parameter theta, which is known, the distribution is known up to the parameter or vector of parameters theta. Because theta is unknown, we use statistical estimation to estimate it or to obtain approximates or estimates for theta that are accurate and or precise with respect to the true parameter. Specifically, we develop a function of the data to estimate theta that has good statistical properties, such as small bias and or small variability. Two common approaches in statistics to obtain estimates for statistical estimation are the method of moments and the maximum likelihood approach. Some classic estimators commonly studied in the basic statistical courses are the sample mean and the sample variance. Specifically, we begin with data x1 to xn and estimate the sample mean by the average of the x's, or denoted x bar. This is called sample mean. For the sample variance, we first center the x's by the estimated mean or sample mean. Then we take the sum of the squared centered data and all divided by n minus 1. We can also construct similar estimator for the skewness and kurtosis using the sample skewness and sample kurtosis as provided on the slide. For both, we need to first obtain estimator for the mean and the variance parameters given the sample mean and the sample variance. Then we center the axis by the sample mean, take the power 3 for sample skewness and power 4 for the sample kurtosis and sum them up. We divide those sums by n-1 and the sample standard deviation to the power 3 for skewness and power 4 for the kurtosis. The mean and the variance are parameters usually of a distribution, where the skewness and kurtosis are statistical summaries of a distribution. Similar estimators can be constructed for other central moments. I will note here that since we use empirical data to obtain estimates of such parameters or statistical summaries, we obtain realizations from the data to plug in this formula to get the corresponding estimated values for one set of realizations. Because every time we observe from the data, we have different realizations, different observations. We do not get the true values for the statistical summaries, mean, variance, skewness, or kurtosis, but approximate values, estimates, which will change with each different set of observed data from the random data. Because of this, we commonly denote the estimators of parameters or statistical summaries with hats, for example, mu hat, sigma hat, and so on. So I will distinguish here between the estimators with hats and the true parameters. We use mu hat for the estimator of mu, and you use this mu without the hat for the true parameter. Because the estimators of a parameter or statistical summaries are functions of the random data, they're also random variables. For example, the estimator of the mean is big X bar, which reflects all possible realizations of the sample mean. If the data are normally distributed, then the distribution of X bar is also normal with mean mu, the true parameter, mu, and the variance sigma squared divided by n, where sigma squared is the true variance of the data. Moreover, if the data are not normal for large sample size n, the distribution of X is approximately normal according to the central limit theorem. The distribution of the estimator for the variance, sigma squared, is provided as on the slide. S squared is the sample estimator for the variance. If multiplied by n-1 and divided by the true variance, the sampling distribution is a chi-square distribution with n-1 degrees of freedom. Based on the sampling distribution of an estimator, we can derive important statistical properties for the estimator. For example, our two important statistical properties are unbiasedness and consistency. Unbiasedness refers to the property of an estimator that in expectation is exactly equal to the true parameter, where consistency means that for large sample data, the estimator is similar to the true parameter, where similarity is in a probabilistic sense. Next, I will introduce the two methods used to estimate parameters in distributions. The first one is method of moments estimation. In this method, we equate the distribution or population moments to the sample moments to obtain equations in the parameters to be estimated, which will be solved for the parameters of interest. To be more specific, we equate the population pth moment to the pth sample moment to obtain this equation. This equation will be a function of the parameters for specific power values of p. We usually consider equations for small power of p, for example, p equal to 1, p equal to 2, and rarely higher. Here are some examples. If we have data from a normal distribution, we want to estimate the mean mu, we equate the first moment to the expectation to the sample mean. Note that the first moment is actually equal to the parameter mu. Solving this equation will give us the estimator mu hat, which is the average of xi's. If we also want to get an estimator for sigma squared, we can use the second moment, which is equal to the second sample moment, which is equated to the second sample moment. Using the first equation where we derived the sample mean, mu hat, we can now plug it in the second equation to get the estimator for sigma squared, which is provided on a slide. Note that the estimator for sigma squared obtained using method of moments is slightly different than the sample variance because here we have n instead of n minus 1. This is the second approach used for estimating parameters. Maximum likelihood estimation, or abbreviated MLE, is the most popular method for estimating parameters for a distribution or a model. The idea is to maximize the likelihood of observing the realizations given the parameters. Thus, if we want to estimate the parameter theta of the distribution of the data, we need to first establish the likelihood function, which in the case of independence would be the product of the density functions for each individual xi's in the data. More generally, the likelihood function is a joint density function of the random data x1 to xn. The likelihood function is a function of theta given the data, and thus, when we maximize MLE, we maximize with respect to theta. Since I mentioned joint distribution, let's discuss about multivariate distribution. It's important to understand the difference between joint, conditional, and marginal distributions. For two random variables x and y, we have a bivariate distribution f of xy called the joint distribution. We can decompose this joint distribution into a product of conditional distribution of x given y times the marginal distribution of y. We write the conditional density as f x bar y. This is also equal to the product of the conditional distribution y given x times the marginal of x. It's important to note that if x and y are independent, then the conditional distribution fx given y is the marginal distribution of x, and the conditional distribution of y given x is the marginal of y. Thus, when we have independence, the joint distribution is going to be the product of the marginal distributions. We can expand this to three variables in a similar way. The joint distribution is a trivariate distribution which can be decomposed in three parts: the product of the condition of the distribution of x given y and z times the condition of y given z times the marginal of z. We can expand this even to n random variables. Similar as with three variables, we will have n minus 1 conditional and 1 marginal. Under independence of the n random variables, this becomes again the product of the marginal distributions. For example, if the conditional distribution of xi given xi minus 1 to x1 has a normal distribution with mean mu I and sigma I squared, and if we ignore the marginal of x1, then the joint distribution of x1 to xn is as on the slide. This particular derivation will come up in some of the models in this course. One of the most important aspects in statistical analysis is statistical inference. For example, hypothesis testing. An example of a hypothesis test is when we're interested in making an inference on a particular parameter theta. Here, for example, we may want to test the null hypothesis that theta is equal to theta 0 versus the alternative that theta is not equal to theta 0. Here, theta 0 is a known null value. We can also have hypothesis testing for distributions. For example, we may be interested to test whether the data come from a normal distribution versus not. In all such hypothesis testing procedures, we always have a null and alternative hypothesis. We often make decisions based on a p-value rather than rejection rules. And in this class, we're going to focus on making decisions based on a p-values. A p-value is a measure of the plausibility of the null hypothesis. P-value also can be interpreted as the smallest significance level at which we reject the null hypothesis, where the significance level is the probability of type 1 error. Another classic statistical inference is through confidence intervals, which involves finding a range of values for parameter theta given the confidence level 1 minus alpha. We get this range by solving that probability of theta being in the range is equal to the confidence level. While this is how we get the confidence interval, its interpretation is more subtle. For example, if we take a 1 minus alpha confidence interval, where 1 minus alpha will refer to a 95% confidence interval. If we obtain 100 different set of realizations from the data, and we estimate the confidence intervals for all the 100 sets of realizations, we'll obtain 100 confidence intervals. If the confidence interval are 95 confidence interval, we interpret that 95 out of 100 confidence intervals constructed with 100 different sets of realizations include the true parameter. That is, 5 of the confidence intervals will not include a true parameter, or least in average. In summary, in this lesson, I provided an overview of main statistical concepts that will be needed for this course. Thank you.